Hello everyone, today we will discuss the concept of descriptive statistics. In order to do statistics, we first need to collect data, then use the data to help us with presenting, analyzing, and interpreting. Presenting falls under descriptive statistics. Analyzing and interpreting falls under inferential statistics. Descriptive statistics involve looking at data from different scales. For example, if we have a data set with 8 points, it will be a great idea to use a coordinate axis to visually represent these points. It's interesting to note that the number 5 appears twice. When we look at these data points on the axis, it's crucial to understand the data's tendency to cluster around a central value. The mean or average is a great way to measure this central tendency. It's calculated by adding all the numbers together and then dividing by the total number of values, which in this case gives us 5. The mean is essentially a measure of where the data is positioned. Now, if one of the values changes from 8 to 40, the average shifts from 5 to 9. And in this value 12 is an outlier, a point that has a strong impact. This shows that sometimes the average might not truly reflect the actual situation of the data. When it comes to outliers, when we're doing the Six Sigma project, we should not just these outliers right away. It's better to investigate why they're there. Sometimes these outliers can show us the opportunities for improvement. In this case of seigniorial, using the median might be a better idea. Median is the number that sits right in the middle of the data. In this case, because there are two 5s, the average of them is still 5, so the median is 5. The advantage of the median is that it won't get affected by changes or skewness on either side of the data set. Its value stays stable no matter how the rest of the data varies. If the total count of a data set is odd, then the median is simply the value that's right in the middle. Another way to describe the central tendency is through mode, which represent the data represent the most frequent. In this data set, the value 10 occurs the most frequently, so the mode is 10. But if we have a large enough data set with many measurements, the occurrence of the same value at the same time is quite rare. In such cases, it will be a good idea to use the mode in conjunction with value ranges. This approach can help us better describe the data. If there are two values occur with the same frequency, the modes will be both. In this example, the mode would be both 3 and 10. In this page, the top data set's average was 5, and the bottom is also 5. However, the distribution of the data is quite different. This indicates that we need to measure not just the central tendency of data, but also its spread or dispersion. From a quality perspective, the bottom data set is better, mainly because it has less dispersion, which usually represents a higher quality level. Now, let's go back to the first example. If we want to measure the extent of dispersion, by looking at the coordinate axis, a natural idea is to use the range, which is the maximum value minus the minimum value. In this case, it's 8 minus 2, which equals 6. Normally, this method is not a bad choice. However, if a single value is too large, it can skew the range significantly. Like now, it jumps from 6 to 11. This is because the range calculation only involves two values. Therefore, unless we're averaging ranges across many subgroups, we typically don't use it to measure the dispersion. Then what the other way to measure the dispersion? Since average value of the data set is 5, if we subtract the average from each number, like 2 minus 5 equals negative 3, and so on, we get 8 differences. These numbers represent each data difference's variance. This seems fine, but because the sum of these differences equal to 0. So, this method isn't feasible for measuring overall dispersion. And because the absolute difference is not commonly used in the statistics, this may not a good idea as well. However, what we can do is to square the difference of each value from the mean, we got 8 numbers, by adding these up, which gives us 28, known as the sum of squares. One advantage of the sum of squares is that it amplifies differences, and also it is sensitivity to variability and won't get impacted by the negative values. More importantly, it is based on the foundation of statistical method. Many modern statistical theories are based on the analysis of the sum of squares, such as ANOVA, regression, and DOE. Thus, it's one of the best methods for assessing dispersion. The sum of squared deviations, often referred to as the total variance, is generated by 8 values. If these values represent the entire population, then dividing the sum of squared deviations by 8 gives us the average variation, known as the variance. Taking the square root of the variance results in the standard deviation. The standard deviation shares the same units as the characteristics it's measuring, making it a natural and popular parameter to show the spread around the mean. If these values represent a sample, then the variance needs to be divided by 8 to 1. We will explain the reason in video number 4. Then, we can easily get the standard deviation, which is 2. It's important to note that standard deviation does not have negative values because it represents the degree of deviation from the center, not the difference. This is the formula for the sum of squared deviations, variance, and standard deviation. Sum represents the sum. Letter capital X represents the random variable values of the population, and lower x represents the random variable values of the sample. Capital N and lower n respectively represent the size of the population and the sample. I equal to 1 means starting the calculation from the first one. It should be noted that, in this video series, we try to avoid using formulas and emphasize understanding the concepts and knowing how to calculate. However, clearly, some formulas are unavoidable. In summary, there are 5 methods to measure the degree of dispersion. They are range, absolute difference, sum of squares, variance, and standard deviation, and these are also methods to assess the magnitude of variation. Variation implies the extent of variability, and variability is a general term for phenomena that cannot produce identical results. In addition to measures of location and dispersion, there is also a concept called relative position, which is assessed using quantiles. Quantiles is, given a set of data arranged in ascending order, there are n-1 points that divide this set into n equal portions. Apparently, each quantile point represents the relative position of a certain size portion of the data. Deciles is a quantiles, which means there are 9 quantile points dividing the dataset into 10 equal parts. Percentiles is also a quantile, which 99 points divide the dataset into 100 parts. For example, the 23rd percentile means that approximately 23% of the data is less than this point, and there are 77% greater than it. In summary, for the p percentile, the portion less than it is p%, and the portion greater than it is 100 minus p%. Percentiles are very important statistical tools, commonly used to mark the positions of cumulative probabilities in various distributions. Another commonly used type of quantile is the quartile, where 3 values divide the dataset into 4 parts. These are marked as Q1, Q2, and Q3. representing the 25th, 50th, and 75th percentiles, respectively, also known as the lower, median, and upper quartiles. Quartiles are often used in creating box plots, which allow us to see the general positions of the data divided into 4 sections, and we will introduce the box plot related concept in the next video. We'll now take an example to calculate the third quartile, Q3, of a dataset. This dataset contains 11 values. First, we arrange them in ascending order, and then we calculate the position of Q3 using this formula, p% multiplied by n plus 1, since p% for Q3 is 75% and n is 11. Substituting these values into the formula gives us a position of 9. Next, we find the value at the 9th position. If the position number is an integer, as it is in this case, we directly take the value at that position. Since the value at position 9 is 89, therefore Q3 equals 89. Now, let's remove one value from this dataset, reducing it to 10 numbers, and recalculate the position for Q3. Applying the formula p% multiplied by n plus 1 with p% as 75% and n as 10, we get a position of 8.25. To calculate Q3 in this case, since 8.5 is not an integer, Q3 is between the 8th and 9th positions. The calculation involves taking the difference between the 9th number, 89, and the 8th number, 86, multiplying this difference by 0.25, which is the decimal part of 8.5, and then adding this result to the 8th number, 86. Therefore, the final calculation is 86 plus 89 minus 86 times 0.25, resulting in 86.75 for Q3. Let's take another example, calculating the 37th percentile. To find the position, we substitute 37% into the formula, resulting in 4.07. To calculate P37, since 4.07 is not an integer, P37 lies between the 4th and 5th positions. The calculation involves taking the difference between the 5th number, 77, and the 4th number, 72, multiplying this difference by 0.07, and then adding this result to the 4th number, 72. Therefore, P37 is calculated as 72 plus 77 minus 72 times 0.07, and we get the final value, 72.35. Let's now summarize what we have learned today. Statistics is a discipline inherently tied to data. For a dataset, we understand its characteristics through various parameters, such as mean, mode, median, variance, etc. Each of these statistical measures has its own strengths and limitations. We also introduced the concept of standard deviation, which allows for a relatively scientific and objective description of a dataset. Similarly, we discussed quantiles, which also possess the ability to describe a dataset's position and distribution characteristics. This is the conclusion of today's video. See you next time.